Okie dokie, folkies. In this screencast, we take a look at something that is cutting edge 1742. We're going to talk about Newton's method for approximating roots of whatever kind of equations, polynomial equations, any sort of equation. We're going to take a look at how we can approximate roots of equations using nothing more than the first derivative. It's going to be an iterative process, which means that one approximation will help us get better approximations if a function is well behaved. So let's imagine the following. Let's imagine that there is some function, call it f of x, and f of x has a root, and that root is right there, and I'd like to approximate that root. But I don't know exactly where it is, so I take a guess. And my first guess is some point called x0. And I figure out what the y value is for that function. And I say, you know what? Functions are really close to tangent lines in small neighborhoods. So if this isn't a root, and I can find out very easily if it is or is not a zero of the function, then let's take the tangent line to f of x at that point, and let's figure out where that tangent line hits the axis. Where that tangent line hits the axis becomes our next approximation for a root. We'll call that x1. We'll go up here and we'll find that where that function value is. If it's 0, great. If it's not, we repeat the process. We take the tangent line, figure out where the tangent line to f at x1 hits the axis. That becomes our next approximation for a root, call it x2, and we just continue this process until we have a root. So let's go back to basics. What is this tangent line? Well, this tangent line is a linearization, and so it's f of x0 plus f prime of x0 times x minus x0. But I want zeros. That is to say, I want where this particular function is 0. So I can solve this. It doesn't take much more than algebra to do that. And so what we get, we kick this f of x0 to the other side. Divide by f prime of x0. Add x0, and so we get that our new x is x0 minus f of x0 over f prime of x0. Now, this x is actually the x1 that's in the picture. And if we were to try to get x2, well, then this would be an x2, and this would be an x1, and this would be an x1, and this would be an x1, which means that in general, oh, that's just hideous. This is going to be something you're going to use. So, in general, for Newton's method, the n+1th guess as to what a root is the previous guess minus the function value at that guess over the derivative value at that guess. Now, if you're a math major, or you're interested in the mathematical sciences, or math is just kind of your thing, then you should know that this comes from somewhere. It's not just, Newton's method hatched from an egg. It actually comes from somewhere. But if you're just, oh my gosh, I got to put something on an index card, this is the thing you put on an index card. So let's do this. Let's let f of x be x squared minus 5, and let's let x sub 0 be 2. In other words, I have this parabola. It has a root. That root is at the square root of 5. It's at the square root of 5. F prime happens to be 2x. And I have a decent first approximation. I have a decent initial approximation. So the first x value that comes through this process is x0 minus f of x0 over f prime of x0. So that's 2 minus f of x0, f of 2, that's negative 1, over f prime of x0, that's 2 times x0, that's 2 times 2, that's 4. That's 2.25. Now 2.25 is a better approximation. Better. But we can do better than that. We can get an x2, a second iteration of Newton's method, and that's x1 minus f of x1 over f prime of x1. That's 2.25 minus, that's 81/16 minus 5 over 2 times x1, and that turns out to be 2.236111, and it goes. So then what? Well, then we look for a third iteration, and we can just keep doing this. So we can do 2.236111 minus, then we've got f of 2.236111. That's, see, this is really small now. That's really small. Over f prime of x2, and that turns out to be 2.236068 dot dot dot, and that's actually a really good approximation. We can get an approximation for a root really quickly if our first approximation is good and if our function behaves well. This is essentially square root of 5. And we could generate square root of 5 by just continuing this process, but we don't need to continue it depending on our level of accuracy. And I'll always tell you what kind of accuracy you need. So, Newton's method can be used to do one other thing. Let's estimate where y equals 3 minus x squared meets y equals radical x. Let's see where those two functions come together. And it's pretty easy if you think of some other function which is 3 minus x squared minus radical x, and we try to figure out where this function has a 0. Because if this function has a 0, then those two graphs will meet. So let's let x0 be something really close to what we think the root is that's easy to substitute. And we know that f prime of x, oh good, derivative of 3, that's easy. Derivative of this is easy. Derivative of this is easy. And so let's do 2 iterations. Let's get 2 iterations done. Let's get an x1. So x1 is x0 minus f of x0 over f prime of x0. And that's 1 minus f of 1 over f prime of 1. And that happens to be 7/5 or 1.4. If I get a second iteration, I try to get something that's a little bit closer to the actual retail price. We do the previous iteration minus f of that iteration over f prime of that iteration, and that happens to be approximately 1.356. And we can continue to generate closer and closer answers well, answers that are closer and closer to the actual solution by continuing this process ad infinitum. So this is Newton's method. It is the kind of thing where we just crank out answers. We've got to know how to crank out answers. And that's all I have for us. So 11 minutes on this is super. Glad to have been able to do it. We will crank out stuff in class next time. Thanks, everybody.